This one, welcome to 8.2 Forces and Momentum, and this is going to be probably one of the longest videos I'll have, and in here we'll detail all the forces that you'll have to learn for the IB physics syllabus. So a force is a vector quantity that describes the interaction between two or more bodies, and it's measured in newtons. And what you'll see often are free body diagrams, which are just simply diagrams that illustrate all the force vectors acting on an object. So for example, if you can see one force acting here and another force acting here, then the net force is equal to 0, considering that they have opposite directions and equal magnitudes, which means the next force is 0, it'll not move, it'll not accelerate, and it'll not go anywhere. The most basic formula for forces is F net equals ma, F equals ma. That, as we'll learn later, is Newton's second law, and that's just the net force. You can calculate it by multiplying the mass and the acceleration of the object. Here, on this case, you can see two vectors that work, together to create a vector sum. You have a vertical vector here and a vector that has a horizontal component and a vertical component that goes in the opposite direction of the vertical component of this vector, force vector. But as you can see, because the magnitude of the vertical component is larger on this one, the net force vector still goes up slightly, but to less of an extent than it would have without just this, and of course also goes in the horizontal direction. Now, there are many different types of forces that we're going to go through. Gravitational force, electric force, magnetic force. These are field forces, and field forces are forces that can be exerted without needing contact between two objects. And you have normal force, tension force, friction force, elastic restoring force, viscous drag force, and buoyant force. And you will learn all the relevant formulas for them as well. Normal force is always perpendicular to the surface that is in contact with the body. So for example, if you're sitting down on a chair, there's a normal force exerted on you by the chair. You exert a force of gravity on the chair exerts a normal force back on you, and because you're not accelerating, the normal force is equal to the gravitational force, as we can see in this example of, a ball on a table. There's the gravitational force for the ball, and then the resultant force is 0 because of the normal force exerted by the table onto the ball. Friction forces, and you typically see friction forces a lot in questions involving inclined planes, but the formulas for frictional force are the frictional force can be equal to or greater than or equal to the coefficient of friction multiplied by the normal force. And the difference here is this is the coefficient of dynamic friction, whereas this is the coefficient of static friction. And static friction, as implied in the name, means that the object isn't moving, and dynamic friction means that the object is moving. And in the context of inclined planes, of course, there's the force due to gravity always acting downwards, but because the normal force is perpendicular to the surface, you can see it's perpendicular here to the inclined plane. And the frictional force is always a resistive force. The friction is always a resistive force, and it's acting in the opposite direction that it would, if you see the resultant force vector between the normal force and the gravitational force, it'll go this way, but the frictional force is a resistive force that goes in the opposite direction. And in the context of inclined planes, you can just remember that the normal force is equal to the gravitational force multiplied by cosine theta of the angle. The frictional force is equal to the gravitational force, Fg, multiplied by sine theta, and mu, the coefficient of friction, is always equal to tan theta of this angle. So tension force is the force experienced by a rope attached to a fixed point where there's a force exerted on the other end. And in this case, there's a string holding together, a rectangular block with a gravitational force of Fg acting upon it. And because the object is in motion, it's hanging perfectly, that means that the net force is equal to 0. So the tension force exerted by the string is equivalent to the gravitational force. There's elastic restoring force, and you'll learn about Hooke's law, which is now the equation FH, the elastic restoring force, is equal to negative kx, where k is the spring constant, and it's just a measure of the resistance of the spring against outside forces. If you need a lot of force to pull a spring apart, then it has a very high spring constant. And x merely refers to the displacement of the resultant displacement of the spring, as you can see here in this diagram. And the reason why it's negative is because Hooke's law, under Hooke's law, the elastic restoring force is resistive to the force you exert. For example, you exert a force to pull it down here. Once you let go, the spring is going to go all the way back up here. So as you can see, it's negative to the direction of the displacement. And always consider what is a limit of proportionality, and you can find the limit of proportionality by seeing a graph of the restoring force and the displacement. You can see where, again, as implied in the name, the proportionality stops here is where Hooke's law no longer works, and you can't calculate the elastic restoring force using this formula. And in general, that just means that there's too much strain on the spring to where the spring is messed up. Now, these are new to the IB physics syllabus, and that's the viscous drag force, which is a resistive force, again, that is exerted on a moving body by surrounding fluids, and fluids just refer to liquids and gases. For example, air resistance is a viscous drag force. And in the case of, and here we have a formula for viscous drag force, which only works for spheres, you should note, but you won't be given any question that asks you to calculate the force for something that isn't spherical. You'll only have spherical objects to calculate for. And it's equal to 6 pi eta r v, the product of all those, where eta is the fluid viscosity, which you'll typically be given, or if not, you can just use the same formula to isolate for it. R is the radius of the sphere, and v is the velocity of the sphere as it goes down. And when talking about air resistance, there's something known as terminal velocity, and that just simply occurs when the net force between the drag and the, I don't know why the text is missing here, but the net force and the gravitational force, the net force is equal to 0, which means that the air resistance, the drag force, is equal to the gravitational force. And that's just simply, you need to consider that. And then we have, last but not least, the buoyant force. And it is a resistive force exerted on a body, also by a fluid, when the object is either partly or wholly submerged in the fluid. The formula for it is buoyant force is equal to rho Vg, where V is the volume of the fluid displaced, rho is the density of the fluid, of the water in this case, and rho is equal to mass divided by volume, as you'll see in the formula booklet in topic B.1, and g, as mentioned, is the acceleration due to gravity, 9.8 meters per second squared. All these formulas that I mentioned are going to be in your formula booklet. Besides, you'll need to remember the inclined plane formulas, where using trigonometry, normal force is equal to Fg cosine theta, friction force is equal to Fg sine theta, and mu the coefficient of friction is equal to tan theta. And that's it for the force.